All right. All right. All right. So we are here today and we are focused all on security, and not just any security. We are talking about quantum security. Yeah, it seems like something way off in the distant future, but quantum computing has actually been a thing for decades. Uh, I live in California, and I can think off the top of my head, like probably 10 quantum computers that have existed since the early 2000s. And this is a hot topic right now because we're seeing a lot of networks being compromised, and not just networks, but just security in general. We're seeing websites get hacked, ransomware, and also you have the debate on decentralization. And here with me is John Woods, the CTO of Algorand. And I don't really think he needs much of an introduction. If they ever do a blockchain Hall of Fame, John is going to be in it.
I don't know about that, but I'm very excited to be here. Thanks, Ďagnam. Thanks for having me, man.
Yeah. So, for like the potato, can you maybe dumb down like what quantum computing is, like on a base surface level? For people who don't understand really what it is, it's really the existence of two things at once, right? So in traditional computing, binary sense, you have like a 1 and a 0, and that's how the codes are written. Right. But in the quantum world, it's not just a 1 or a 0. You can actually have like a third state, essentially, where both 1 and 0 exist at the same time, which is kind of weird.
Right.
Can you maybe simplify that maybe?
Totally. So I'll try to keep this relatively short, but like the reason we use 1s and 0s in computers, I mean, I think first that's something you got to think about. Why is that? Why are we using 1s and 0s rather than letters and decimal numbers like 5, 10, 15, 20? The answer is because, I think the answer is because processors inside computers, like the CPU, the brain of your computer, and your graphics card and all the bits and pieces inside your computer, they operate with voltages. They operate with electrons flowing through them. And so voltages represent 1s or 0s really well, because we can say, 3 volts. Sorry, that many fingers is 3. 3 volts is a 1, and 0 volts or absence of a voltage is 0. And so that's why 1s and 0s or binary became, so ubiquitous within computing. It's because we use voltages to represent 1s and 0s. And then those 1s and 0s can be interpreted by the computer to be video or pictures or audio, or indeed just data like spreadsheets and things like that. As you quite rightly said, quantum computers are a new type of computer, and they don't just deal with 1s and 0s. They deal with what are known as qubits rather than bits. So 1s and 0s are bits. Qubits are where you have a 1 or a 0 in some kind of state of superposition. And what that means is each qubit has a probability of being a 1 or a 0. So maybe it's a 30% of 1 and a 70% of 0. And that may sound a bit confusing. You might be thinking, well, don't computers need 1s and 0s to be quite definite in their state in order to represent media? I mean, if you were playing, an MP3 or a video on YouTube, and the 1s and 0s came down and they were in an indefinite state, they were in a probabilistic state of 30% 1 and 70% 0, that wouldn't be very useful in the context of YouTube. Your video would be all over the place. But it turns out, in terms of cracking certain cryptography, this idea of a 1 or a 0 having a probability is very powerful. And so, essentially, cryptocurrencies like Cardano, like Algorand, like Ethereum, Bitcoin, Monero, etc. These cryptocurrencies use modern cryptography, which uses certain algorithms, the elliptic curve discrete logarithm problem, or, for example, in the case of symmetric algorithms, things like AES or 𝘂𝗃𝗀𝗃. And these algorithms Another great one, of course, is RSA, which uses prime factorization as its core algorithm. And it turns out these quantum computers that I described with these qubits, they can attack these modern cryptographic algorithms and break them. And so what does that mean for you, the end user? The answer is, I can steal your coins, yo. And that is not good, of course.
Right. So I've got up here. So for those who might not know, if you're really into Algorand, you probably already know this. But for those who don't know, you guys are already like quantum ready because you have this Falcon, right? And so can you maybe talk about Algorand's approach to post-quantum readiness and what makes it different, as you highlighted, from other blockchains, and like how crucial is this for blockchain to start preparing for quantum computing right now, and how do you see the influence in the industry for the next 5 to 10 years? And lastly, I'll sort of emphasize this, like, I don't think many people know. Everybody talks about how decentralized Bitcoin is, right? But Bitcoin is not a quantum resistant blockchain.
Not at all. Not at all. So, okay, first I would like to say, just like I did when we were talking about the bits and the qubits, just to bring it back to fundamentals, there are different kind of like parts of the cocktail in cryptography, right? There's like the digital signatures, there's the hashing functions, there's encryption, and these different algorithms are broken to various degrees. So asymmetric cryptography, things like elliptic curve cryptography that we use to sign transactions in Bitcoin, Cardano, Algorand, that algorithm is smashed wide open. So digital signatures are toast. Our current ones are toast in a post-quantum world. So we have to move to post-quantum digital signatures, and that's what Falcon is that you just showed, and I'll talk about that in a second. But there are other parts of cryptography that are less broken. So hashing functions and symmetric encryption, like AES, etc., they are essentially, their strength is it's the root of their current strength. So the square root of the current strength. So they're weakened, but they're not destroyed. And so really, quantum computers have two main algorithms that attack modern cryptography. For the asymmetric side, so the digital signatures that we use to move Bitcoin and move Algorand, they smash it wide open. They reduce the strength to something that is basically the security is eradicated. But for the hashing functions that are used in Algorand, Cardano, and in Bitcoin, and for symmetric encryption, as I mentioned earlier, the strength of the algorithm is essentially square rooted, which turns 256-bit strength into 128-bit strength. So 128 is still strong. So on this side of the house, in the symmetric / hash function side, we think we're okay. But on the other side of the house, where we're using the elliptic curves and the RSA, and these are used absolutely all over the place in cryptocurrencies, every time you sign every time you move money, every time you send Bitcoin, every time you interact with a contract on Ethereum, every time you deploy a new asset on Algorand, doing any of these things, dropping an NFT on Cardano, you're using these elliptic curve primitives on this side of the house. And so we have to fix this stuff because this stuff is just going to get smashed by this new quantum stuff, by this new quantum computers. And so the two algorithms that I was talking about on this side, we have Grover's algorithm that is a quantum algorithm for trying to reduce the strength of this crypto over here, the symmetric stuff. And over here, we have a thing called Shor's algorithm, and that is the quantum algorithm that attacks elliptic curves and RSA, the stuff that we care about. And so we look at elliptic curves. Bitcoin famously uses the 𝗚𝗵𝗽𝗁 curve. Cardano and Algorand, as an example, because I know both of them quite well, they use the Edwards 25519 curve. But both of these elliptic curves on the Bitcoin and the Algorand and Cardano side, they need to be upgraded in order to be secure in a quantum context. Now, there are a bunch of different places that you look at a blockchain and you say, well, I need post-quantum. So typically, the places are, one, for your accounts. So people have their public key, their receive address, and then they have their private key that they keep on their ledger, or they keep written down in a drawer, or they keep on a cold wallet or whatever. We need to inject post-quantum into that account structure because signing, the digital signing of moving of funds needs to be quantum secure. That's number one. Number two, we need to secure the history of the chain. So all the stuff that's been done, right? The transactions from yesteryear, the transactions yesterday, the transactions 4 seconds ago, the transactions at the Genesis block, 5 years ago for Algorand, whatever, 12 years ago for Bitcoin, those transactions all the way back in the chain, they all need to be secured. That's another place. And then I guess specific to Algorand and Cardano, just because again I know them very well, the consensus algorithm uses elliptic curves. And so the VRF, the verifiable random functions at the heart of Algorand that let it have instant finality, that let it do its great stuff, they too need to be given a quantum upgrade. On the Bitcoin side, actually, the consensus algorithm using SHA-2 does not require this, as far as I know when I last looked at it. So that's a third place. And so Algorand has started the journey using Falcon, a post-quantum signature scheme. And what we've done is we've addressed point number 2, the history of the chain. We've gone back to all those transactions, all the way back to the Genesis block, and we've stamped them with this post-quantum shield, so quantum computers can't attack them. But we still need to do 1 and 3, right? We still need to fix not fix because it's not a problem just yet, but we still need to address the threat of quantum computers on the accounts and quantum computers on the consensus mechanism, the VRF. And so where we've currently employed Falcon here, as you have on the screen, I think sharing with the viewers, this fast Fourier lattice-based compact signatures over ntrue, an interesting mouthful there, but what it essentially does is replace the 2-dimensional Cartesian plane of elliptic curves with an n-dimensional lattice-based scheme that quantum computers cannot attack as readily. And so we believe that Falcon, and so does NIST and some other organizations out there, we believe that, so NIST is like a government body in the US that checks crypto for correctness. We all believe that this Falcon post-quantum signature scheme using lattices is bulletproof in the face of post-quantum crypto. But of course, there have been historically many cryptography schemes that we all, as academics, engineers, cryptographers, applied cryptographers, felt or thought was secure, and later we found out that it wasn't secure. So right now, as far as we know, theoretically, this scheme is close to the best that we have in the face of quantum computers. And if a quantum computer was to exist in the morning and attack Algorand's chain history, it would not be able to affect the transactions that have already taken place.
Yeah. So, can you maybe dive into like a couple aspects of this about Falcon and the readiness as you were talking about? So, like, what does the block size have to do with it? So, like, on surface level, one thing that like didn't really make sense to me initially is having a small block size is what you would want. So why would that be like having like a smaller key and size signatures be advantageous versus like a bigger?
Yeah, so I think so this stuff doesn't really come into the block size so much, in the sense that like the blocks have all the transactions in them and how big are the blocks. The blocks on Algorand are about 5 megabytes. I think on Bitcoin they're about 1 megabyte, I guess, but they are that doesn't really get affected so much. But rather, what's important is, like, right now you're writing down 24 words, right? When you open an account on Bitcoin or Algorand, you got to write down your 24 words, because a private key for an elliptic curve is 256 ones or zeros. And so 256 ones or zeros is 32 bytes. And we can represent 32 bytes of data as 24 English words, because each word is about 11 bits. So we can write down 24 words. The problem is, for the smallest Falcon key, right, the smallest private key for one of these lattices, we'd have to write down 700 words or 800 words. And so that's not practical. And so the problem is, in order to beef up the security against these quantum computers, you tend to need to use more exotic mathematics. And sometimes those more exotic mathematics require that a private key will be much larger. And so in the case of Falcon, as far as I remember reading, the private key is essentially like a vector, shortest vector between 2 points. And so from the basis to a point within this n-dimensional lattice. And because you're dealing with these n-dimensional structures, so not 2D, not 3D, not 4D, but potentially 12-dimensional structures, which our human brains can't even really imagine thinking about, the size of the data for the private keys is much bigger. And so that presents a usability problem. So like, how do we allow the average person, a normal person, a user, a normal person on the street, who's not a computer scientist or some kind of whiz kid, how do we allow those guys to use these technologies? Because they need to. This technology has to be for everyone, right? It can't just be for computer geeks. But also not have to have the burden of writing down 700 bloody words, right? It doesn't work. And so what we're doing at the moment is, by securing the history of the chain, no one has to remember the keys, because it's the network itself, it's the protocol on Algorand right now, and the protocol runners that are holding these post-quantum keys. So the average user is not the one holding the key to secure the history of the chain. Okay, the average user is not the one who has to know the private key to sign the history of the chain in a post-quantum way. But when we move to a place where just spending your algo or spending your Cardano, when you want to move your ADA from here to there, you want to move your algo from account A to account B, when we want to do that in a post-quantum way, we do need the end user or the average person to know, have knowledge of a post-quantum key. Now, of course, that'll probably be on their mobile phone or whatever, and that's great. And your iPhone, your Android phone will have no problem dealing with that. But to back up that key, and of course, we always say to ourselves, it's very important to back up your ledger phrase or your private key phrases, to make sure that if you lose your device, that you don't lose access to your crypto. We need to find a better user experience than writing down 700 words. And so that's one of the challenges. But there are other technical challenges. The size of the signatures are bigger. So elliptic curve signatures are very small. They're about 64 bytes, I think, depending on the curve that you use. That's quite small, doesn't take up much space in the block. If we move to Falcon signatures, they're megabytes in size, right? They're about, well, it depends, but they're an order of magnitude larger in terms of the number of ones and zeros you have to store in order to put those signatures in a block. And so we have to find ways to scale those quantum technologies to a place where we get the security, but they don't affect so much the scalability or the usability of the protocol.
Yeah, and scalability, ties into this, right? Because you want it to be fast enough that, computers can both access this and verify it. And you could even potentially do this on a phone.
Precisely.
But then,
but
then you want to be flexible too, right? So like, would certain networks, because right now, I mean, it's just a fact. There's networks that are not, have zero quantum readiness. And quantum computers are out in the world right now. So potentially all these networks are already vulnerable.
Well, what I would say is you are right that we do have quantum computers out there in the world, and then they can run these algorithms that I talked about before, Shor's algorithm and Grover's algorithm. And if you Google those, you'll see write-ups on Wikipedia about them. But those quantum computers don't have enough qubits. They don't have enough raw power to really affect these algorithms. And in kind of a simple way, it's a bit of a generalism, or maybe not. It's a bit of a casual way to say it, but we're kind of we're back with the Nintendo Entertainment System or the Game Boy, right? We're back we're on the emergence of modern quantum computers. It's going to take a while before the Nintendo, the Game Boy, the SNES, the Mega Drive, or what was it called in the US? I think it was called like Master System or something like that. It's going to take a while before those consoles, graduate up to the PlayStation 5, right? And so when we have PlayStation 5 level quantum computers, then we have a problem. Right now, those quantum computers are still babies, and so they're not able to. They can run these algorithms, but they can only run them against small keys. They can't really attack the production grade crypto that we use today. And so, but the question really is, as Dagnam is, how long before governments or adversaries, whoever they are, entities out there, have access to a quantum computer which does have enough qubits in error correcting qubits in order to run these algorithms that I described against modern crypto, like a Bitcoin key, a Cardano key, an Algorand key, and steal your coins or cause problems with the networks. And that could be, I mean, people have different estimations on it, but some people say it's 5 to 7 years away, which is a short amount of time to get ready. And so Algorand's not ready right now fully. We still have work to do. But as you quite rightly said, most networks out there have nothing done on this, from what I can see.
Yeah. Algorand's right up there. And I know the other, because you were mentioning how splitting up the keys is, key to this. One of the DREC partners, Constellation, one of the reasons why they got government contracts is because I'm not exactly sure how the network achieves quantum proofing. I think from my own reading and stuff, I think it has to do with the structure of the network itself. Like, because it's a directed acyclic graph, that adds some sort of inherent quantum resistance. But is any network essentially, could any network implement like post quantum cryptography and secure themselves?
Right. So, yes, I believe so. Like, it depends on the architecture and the structure of the cryptocurrency. Certain networks have made certain trade-offs around decentralization and around speed. Like, as an
Uh-huh.
example, Solana has a very quick block time of, last time I checked it, I think it was like 400 milliseconds or something. And maybe I'm off base with that, but I think that's what it is. Let me just check it. Live checking it. Yeah. Look, 400 milliseconds. Cool. Yeah. Okay. Good. Wasn't wrong. Okay. And so the question is, hey, is that enough time? Is that enough time to take the block full of things and do my post-quantum checks? As you said, all transactions in a block have to be verified. Right now, we use elliptic curves. They're super, super fast in verification. They take, fractions of a millisecond. You can get it done really, really, really fast. Do we have time to verify Falcon signatures or equivalent? Falcon's not the only way to do post-quantum. That's a lattice way. You can use multivariate schemes, code-based schemes, hash-based schemes. There's other ways mathematically to do post-quantum cryptography and achieve a digital signature. But one thing they have in common, they're all slower than elliptic curves that we use right now ubiquitously across the crypto industry. And so, a lot of networks might have serious issues with this. Bitcoin won't. I think that has a very obvious path to move from K1, the curve, to some digital signature scheme, which is post-quantum. It might have some trouble securing the history of the chain, but I think it'll probably be okay because it doesn't use the VRF. Cardano, the same. Cardano basically has the same problems as Algorand. It needs to solve the same problems. And so Algorand can solve this, and we know we can solve it. So Cardano will be fine. Because, again, the block time on Cardano, I think it's like every 5 seconds, maybe, I think, is a slot time. I think last time I looked on Cardano. And so that's fine. We have the time there to do the things we need to do. But I think some networks will struggle to do this. But it's not just in sprinkling your post-quantum stuff on top of your network and can my network kind of absorb this and deal with it. But it's also the hardness of the engineering around both moving your user base to use an account scheme that is now, maybe a different type of key, a different kind of way, user experience, but also just, the heavy lifting of the mathematics and the cryptography and the implementation of this stuff. Like, it's really hard stuff. There's a handful of people out there, and I mean a handful, there's like, 8, 9 people globally who truly understand this stuff. And I'm not one of them. I have a good idea how it works, but I'm not an expert. People like Chris Picart, who works with Algorand on our post-quantum stuff and did our state proofs, which are our post-quantum history of the chain thing. Chris has been, he's got a book called, A Decade in Lattices. It's like, Austin Powers, lattices and me, this kind of thing is my bag, baby, So you need one of these guys or gals out there to help you with this stuff. And there's only a handful of them. And so it's an emerging field of mathematics and computer science, and it's tough. And so at large, I think the industry will get to a place where we're good and we are secure, but some blockchains won't make it.
Yeah, and can you maybe, because you talked a little bit right there about state proofs, can you maybe elaborate a little bit about how Algorand's state proofs protect the blockchain from historical data?
Yeah.
From potential quantum attacks? And then, since Algorand's in the DREC, this kind of maybe could tie into how state proofs can facilitate cross-chain interoperability in like a post-quantum sense.
Yeah, so state proofs are our kind of marketing name for a technology on Algorand that issues a cryptographic attestation of all of the transactions that have occurred within a certain window. And so at the moment, a state proof is issued on Algorand every 256 rounds. And so our rounds are about every kind of 2.8 seconds. So it's about every 11 to 12 minutes. So every 11 to 12 minutes of real time in real life, a new state proof comes on the chain. Now, they do two things. First, they provide a small, I think it's about 4 megabytes. They provide this small 4 megabyte file. And this file is like a cryptographic proof of all of the transactions that have occurred during the last 12 minutes. So you can take any transaction in that batch and take the state proof and validate that it was correct. And so this is great because if you're another blockchain, you don't have to get all of the data from Algorand to verify it because that's like gigabytes and gigabytes of data. Instead, you can take one of these state proofs. It's succinct, it's small, and then just using that state proof, you can assert whether or not a certain transaction is in the chain. So this is a very elegant, mathematically sound, decentralized way without any chain of validators or Guardian network or any of that bullshit, in a trustless way to be able to verify the state on another chain. And so what is the natural product that you can use that for? Bridging. If I can trust your state by just getting a little file, and you can trust my state by just getting a little file, and we don't have to look at each other's big fat blockchains, we can just look at the little file, and then we can be like, you know what, that has been locked over there, I'm good. And then you look at mine and go, yep, that dude did do that swap, that's good. Then we can do cross-chain stuff really easy without having any extra fluff. Trustless, disintermediated, distributed communication. Super cool. As a side effect, though, we chose as an engineering team to sign the state proof with a post-quantum primitive. And what do I mean by that? We said, this is an opportunity. We're going to be stamping the chain with this like validation of all the transactions every 12 minutes. And we can speed that up, by the way. 12 minutes is a bit slow, I think. And I want to be fair about these things and authentic about them. So if you're doing cross-chain bridging, having a 12-minute window where you're radio silent and then you get your new data, 12 more minutes of radio silence and then new data, that's not a great experience. So we need this thing to be every few minutes, right? But at the moment, it's every 12 minutes. We thought, this is going to be checkpointing the chain with this like stake in the ground, bang, 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 every 12 minutes. And the first one that goes in will validate every transaction from Genesis all the way up to the modern day. And then we go on every 12 minutes. And so we're like, this is a great opportunity. Don't sign these things with like normal elliptic curve things, like we do with the blocks, right? We sign the blocks with elliptic curve primitives. Let's use post-quantum here. Because if we use post-quantum, the side effect is that we have quantum secured the history of the chain. Because if we basically have signed the state from Genesis, the very first block, all the way to the real time right now current block as of like today. Now and if we sign that state with Falcon or any other post quantum signature, we use Falcon because we think it's the smartest one. Boom, we've just quantum secured the history of the chain, and so that's why we chose Falcon. So it was kind of a 1-2 punch. We wanted to interop. We wanted to do it trustlessly. We like this idea of proving the state of Algorand. We branded it state proofs because we think that's a cool name. And then we used a quantum primitive so that we could say, hey, we've just quantum proofed the history of the chain.
And so this kind of leads perfectly into my last question as we're rounding out the time here. But like, how do you see the adoption of these post-quantum standards impacting regulatory compliance and the future of blockchain, and not just the financial sector, but in all real world stuff? Like you guys in particular, I've just been kind of blown away about all the real world adoption that you guys have. You have all the agriculture stuff.
Right.
You've got gold. You've got MasterCard using it. You've
real estate.
The travel app. I mean, it's crazy, and I can't. I have a hard time believing that you're going to convince somebody like an American Airlines to use your network if it doesn't have some sort of quantum resistance part, because nobody wants to get their stuff hacked.
Right. And so I would say it's going to be a little while before we see these companies and their chief information security officers or whatever really grok this stuff, because this is at like, it really is at the bleeding edge of cryptography and the bleeding edge of mathematics. I mean, even if you go out there and you're like, hey, I want to implement this stuff in American Airlines, like the libraries to do it, like the code out there on the web to implement this stuff is few and far between. The support for it is again few and far between, and you really need an expert in this stuff to properly implement it. And so I guess blockchains always kind of paved the way for modern cool crypto. I mean, we see that with many things, from zero knowledge proofs all the way to pairing based curves and other kind of groovy things that blockchains seem to kind of like just try to, you know, drive out the kind of absolute, you know, cutting edge of technology. But it absolutely will come. There will come a point where FedRAMP and, you know, your HIPAA stuff and all your different kind of like standards bodies when you're dealing with personal information or medical information, or even just governments, right? Like FedRAMP's a regulation around the standards that you have to have around ISO and all this kind of stuff in terms of like your cryptography being FIPS compliant and all that kind of stuff. We will absolutely see FIPS adopt PQ, post-quantum crypto. And I think we'll absolutely see these other companies fall in line as well. But again, it may take some time. It's okay though, because for those companies, most likely their data is really siloed inside some database in a warehouse somewhere, or protected behind some Amazon firewall. And so the data is not floating out there for everyone to see. And so you have to first get the data before you can attack it. And for those companies, largely they'll be using symmetric cryptography. They'll be using a single private key, which uses a symmetric algorithm, which is still strong in post quantum. After quantum arrives and quantum computers are here to attack symmetric keys, they are still strong. They still have 128-bit security. But the same cannot be said for blockchains. Why? Two differences. One, blockchains are public by definition. All that data is out there in the public domain. It's completely out there. Every blockchain can be read by anyone globally, unlike the data that maybe sits in American Airlines. And number two, blockchains essentially, except for hash functions, exclusively use elliptic curve primitives. And so they are part of the side of the house I mentioned earlier that can just get smashed wide open by this new quantum stuff. So we have a double problem. And so we need to sort this stuff out. And so at the very least, I would say most CTOs or tech leaders or tech leads within these various blockchain development teams should be looking at this.
And so, as you can maybe send us off, like outside of you know, the quantum stuff, like what are the next exciting things on the roadmap for Algorand that people should be looking forward to?
Yeah, totally. You know, I think I've been at Algorand Foundation for over 2 years, nearly 2.5 years, I guess. And it's been a great journey. I think only now we're getting the recognition that really we deserve. I mean, you know, there's lots of other networks that do it well. Cardano is a great example, but they have recognition, right? They're in top 10, and so people see them as a major player. We're only just starting to get, I think, the recognition that maybe Algorand should have, because of some of the engineering it's done, but also in terms of like the quality of the user experience on the chain. And so to reinforce that adoption and that recognition, we're going to be releasing some pretty significant stuff that we're going to be pushing out fairly shortly. The first is we're going to be, again, making our developer tools even better. So we started off last year doing you know, tools for build, test, and deploy, truffle, hard hat style tools. We brought Python, the programming language, to Algorand as a mainstream language rather than using 𝗙, which is some, you know, low-level language. This year, we're going to be bringing TypeScript, another language that's loved globally, and also line-by-line debugging. So you'll be able to, like, you know, put a breakpoint and like do your line-by-line debugging just like you can in VS Code for a regular programming language like Rust or Go or C or whatever. On top of that, we have a gargantuan update to our network topology. So we're going to be changing the way data flows from away from relay style networks into a peer-to-peer style network. So nodes on Algorand will talk directly to each other. So during consensus operation and during propagation of transactions, we will now have this like cockroach style protocol that cannot be disrupted. So no one can put a stop to the flow of the data because the data flows like a spider web throughout the network. And then finally, also in early 2025, well, late 2024, early 2025, we'll be rolling out consensus incentives. So we're going to be branding this externally as staking rewards, which is not actually known yet, but we'll be pushing hard on this, staking rewards is the name. But essentially what it is that right now you make a block, you mint a block on Cardano, you get paid. You mine a block on Bitcoin, you get paid. You mine a block or mint a block on Algorand, you get nothing. And so the problem with this is you don't get a ton of people who want to run computers for free, altruistically, despite maybe there being a point that maybe people should want to stake to secure their own funds. So we're modifying the protocol, and the protocol will now reward people who stake and who propose blocks, or mint, mine, whatever word you want to use, who create blocks. And so the rewards are going to be quite high, and then over time they will drop off, like Bitcoin does, kind of on a function. But for the first few years, they're going to be pretty juicy, and so it's going to be a great time to get involved with Algorand. Maybe swap some of your existing, Solana tokens into Algo. Get involved and start staking. There's no slashing, and so. Yeah, it's an interesting time. So some big stuff coming up. I think that's philosophically changing how we do Algorand things.
Well, there you go. You heard it. That is a mic drop game changer right there. Staking on Algorand.
Yeah.
So yeah, I'll definitely be looking forward to that, and would absolutely love to participate in it if I have the ability to do so.
Absolutely.
Yeah, I'm gonna have to just kind of wrap my brain around that. That was a good one to leave off with. Thanks for taking the time. And everybody, this will be up and playable later on YouTube and X. It's live now, but we can record and share, and keep an eye on the comments too. So just don't forget to just leave a comment. And until next time,